Oh, should I start again?
No, it's fine.
It's okay. Yeah, and this is the reason why coarse-graining has regained a lot of attention in recent years. And the idea is basically, let's take a simple example. We look at a school, we have two classes full of students. Each student will be represented by a node and differentials between them by edges. And then what we can just do is to represent each class by one entire node. Because coarse-graining just tries to identify groups of vertices which are similar in some way. And then we have essentially a representation, a simplified representation of one node here, a connection across those. And the question, of course, now is such a simple graph able to represent the large-scale properties of the original graph? And this is the question that we try to answer today. And for that, we look at something from physics, the renormalization group. The renormalization group is one of the most important frameworks in physics to understand how macroscopic properties emerge, and it has allowed us to understand phase transitions and criticality and scaling behavior in systems like ferromagnets. I won't go into too much detail here, but if you have any questions, ask me afterwards. But the idea, so the essence behind it is essentially you have your system, you coarse-grain the system, and in the sense that you remove degrees of freedoms, and then you rescale the system in order to get an effective representation at a higher scale. And what this means is that this effective representation is now an accurate representation of the original system for large scales. And this is exactly what we need. The problem, however, is that we cannot straightforward apply this to graphs. Because in graphs, we need geometric distance. So for the renormalization group, we need geometric distance. And for graphs, we would need that too, but it's very delicate to define this in graphs. And in many cases, we also need translational invariant, which is also a very delicate thing to define in graphs. So for that reason, we look at something else. We look at diffusion. So the thing is with diffusion, we can also think of it as a notion of distance. And this is because the less time it takes for something to diffuse from one point to another, the closer it is. And this makes a lot of sense for our purposes because in many systems that we are interested in, closeness in a geometric sense is not necessarily an indicator for interaction strength. For example, in a magnet it is, you have the spins that are next to each other, and these are of course the ones, let's say in an Ising model, which are interacting the strongest with each other. But in these systems like, let's say the brain, this is not the case. For example, with neurons that are close to each other, these are not necessarily the constituents that are interacting the strongest with each other. Because, they can form connections across distance. So what we propose here is essentially a coarse-graining and rescaling framework, which follows the idea of the Wilsonian renormalization group, but without relying on geometric closeness. And it gives us an effective representation of the original graph while preserving the macroscopic structure and also the macroscopic dynamics of the original graph. And to understand how we do this, the first thing is we look at diffusion on the graph. And I think this equation is very familiar to most of you. It is just a diffusion equation on the graph. It describes how diffusion behaves on the graph. And it's governed by this L here. This is the graph Laplacian, the combinatorial graph Laplacian. And it's defined as D minus A. So D is the degree matrix, A is the adjacency matrix. And for the ones in the room that are not familiar with it, it is just the heat equation, but not on the Euclidean space, but on the graph. This is how you can think about it. And I think it's now straightforward to see that this equation is solved by this matrix exponential here. And this gives us the following solution of the diffusion equation. And the matrix exponential is also referred to as the heat kernel. And since a long time, it's used for spectral clustering or clustering in general, just because the entries of the heat kernel consider each diffusion path from one node to another and weight shorter paths more strongly. So this gives us essentially a notion of closeness, and hence the name kernel. But what we do with our work is that we do not rely on it. We look at the graph Laplacian itself. And the reason for this is that the Laplacian will tell us not only how to find effective vertices, but also how to adjust the interactions at different scales between those new effective vertices. So, to obtain a representation of the system in the sense of Wilson, so in a renormalization group that preserves our large-scale properties, we need to rescale the interactions between the new degrees of freedom. We cannot just obtain new degrees of freedom between them and leave the connections between them as they are. We have to adjust them. And to understand why the Laplacian tells us how to adjust the interactions, we look at the spectral decomposition of it. So we just re-express the Laplacian in terms of its eigenvalues and eigenvectors. So U here is a matrix of eigenvectors, and capital lambda is a matrix, a diagonal matrix of the eigenvalues. And what this simply is, it's a transformation of the coordinate system where before, where the Laplacian was defined as the degree matrix minus the adjacent matrix, it lived in a space spanned by the standard basis vectors, but now it lives in a space spanned by the eigenvectors. And the beautiful thing now is that these eigenvectors tell us something about the graph structure at different scales. So let's look at the first eigenvector here. These are the entries of the eigenvector, and each of them represents a node. And we see this tells us that from that perspective, everything is the same. So all nodes are the same. You can think about it intuitively. You have a graph, and you walk away as far as you can, and what you only will see is just one node. And so everything is the same and can be contracted. If we move one step closer, we see a bit more detail. So we would say something like two nodes. So this second eigenvector associated with the second largest smallest eigenvalue will tell us now how to partition the graph into two. This is also referred as the Fiedler vector, and there are a lot of results, a lot of rigorous results, how to do spectral clustering with that. But we can go on. We can look at the eigenvectors associated to larger eigenvalues. And what we see is very much in the Fourier sense that the eigenvectors play the role of frequencies or energies, and the eigenvectors then get rougher or smoother. So the larger the eigenvalue, the rougher the mode, and the finer the partition of the graph. So, given we are just interested in the macroscopic behavior, given we're just interested in the perfect timing, given we are interested in the macroscopic behavior, now we can just remove the modes that describe the large scale and the fine-grained structure. And to justify this, we can look at timescale separation. And if you want to learn more about this, I recommend the book by Struberts, and there's also a beautiful chapter in the book by Renaud and Michel Schaub about timescale separation. But all we do now is essentially we just remove the modes associated to the larger eigenvalues. And the question, of course, now is we have a graph with n nodes. That means we have a graph with n eigenvalues. What are the eigenvalues to look at? So what are the scales that are interesting to us? And we define them essentially as the scale which separates the first k-smallest eigenvalues from the remaining one. So it's essentially just a gap in the spectrum of the Laplacian that defines our characteristic scale. And what this now means from the perspective of timescale separation, if we were to insert this Laplacian into the solution of the diffusion equation, we would see that after long enough time, the modes associated with high eigenvalues will decay faster, so they will become negligible at certain times. And this is what we essentially use now. Because if we now look at the first k modes and the remaining ones, after times that are larger than the inverse of the first one we threw away, we know that the corresponding modes will be negligible. So this justifies what we do here. And this now allows us to write down the following Laplacian, which just sums up the eigenmodes and eigenvectors up to our spectral gap. So, and this is supposed to describe the large-scale diffusion after this time. And we can even define a bound on this. We again, we just put in the full Laplacian into the solution of the diffusion equation. And here we put in the coarse-grained Laplacian into the solution of the diffusion equation. And what you see is that we can upper bound this by this term. This is the initial error which arises from leaving out the fast diffusion modes, and the decays exponentially with time. So this is quite good. But furthermore, the entries of the Laplacian also tell us now how the structure changes at different scales. Because if we look at one entry of the coarse-grained Laplacian, we see that it's essentially a weighted average of cosine similarities between two vertices. And the weight here is the eigenvalue. And this is simply because we saw on the previous slide that these eigenvectors tell us something about similarities of nodes at different scales and how to partition the graph at different scales. And now we just have a product between them. So what we get here, this is an outer product, is a similarity matrix essentially. And we just sum that up to our spectral again. And this gives us the average similarity of two nodes in this case.
So that these entries can be negative.
Yes. So exactly. So these entries can be negative and it will be a full Laplacian. So it's really a similarity matrix. And this is the right point now, because a negative entry in this Laplacian or an entry of 0 will now tell us that at the given scale, these two nodes are dissimilar. But if it's positive, like in the cosine similarity, it will tell us that these nodes are similar. And we can now use that to define a heuristic contraction procedure. So we'll summarize it here. I think I can, let's zoom into it. Okay, basically this is the original graph here. We compute our Laplacian, we plot the spectrum, and we will see that the first three eigenvalues are well separated from the rest. So we just keep the first three eigenvectors and corresponding nodes. And this is then the graph associated to this coarse-grained graph Laplacian. As you see, it's full, the red edges mark negative edges, and the blue ones are positive ones. So what it now tells us is, if we were to assign these edges to the original graph, is that these nodes here are all similar from our perspective and therefore can be contracted. And these nodes are dissimilar and cannot be contracted. So what we do is exactly that. We're left with a graph with three nodes with new weights between the new effective degrees of freedom. And this will, for now, just tell us the large scale diffusion.
Yep. Why are we using the combinatorial Laplacian? Because in spectral clustering and usually when you do this kind of stuff, you use the degree normalized.
Yes, exactly.
So why do you use the combinatorial?
So technically you can use both, but the results are very different.
Yeah.
Because this one, of course, then takes the degree. So by degree normalizing red, you get intuitively rid of things that tell you, okay, you get the diffusion flows more likely into high degree nodes, right? And this gives you sort of a view of your structure, if this makes sense.
Yeah, when you do this one, like I've done this in brain networks, and if you do it without degree normalizing, you basically get modes that look like just one node.
Exactly.
Whereas when you do it otherwise,
Yes.
you end up like two sides of the brain, four sides of the brain. Like it looks like when you do it with the normalized version.
Okay, but
Yeah.
But I think we get something because we showed also in the brain. That may
In these examples, the graphs are very maybe irregular, right? So do you have like a lot of heterogeneity for the nodes or not?
yes, we have a lot of heterogeneity for the nodes.
Is that? Yeah.
This is very dense.
I mean, it is very dense. You have
Yeah.
organization.
Yes.
But it's quite typical to use the normalized.
Yeah, I know. Yes. No, yeah. As I said before, usually the Fiedler vector, right, is used to do the partitioning. But in this case, we don't, because the motivation behind not using it very much comes from physics, in the sense that the combinatorial graph Laplacian will be, in a sense, the Green's function of your field. And this will be like, if you look at a Markov random field, a Gaussian Markov random field, you will get the combinatorial graph Laplacian if you would discretize the field. This is the motivation behind it. But we also look at the renormalized Laplacian, and we can do it, but we get completely different results. But I don't remember what were the results for this example. I have to check. But okay, I think there will be a brain example maybe that makes it also clearer. Yeah, so what we did until here is just the coarse grain. So remove details of the system. And what we now have to do is we also have to account for the fact that because of removing the details here, there's something missing. So this graph cannot be compared to this in a diffusion sense. So what Wilson now tells us is, in order to compare them, we have to rescale this Laplacian. And what that intuitively does, so I think I'll show this. What it intuitively does, so let's look at a graph like this. Our coarse graining procedure would now give us something like this. So this would be represented by this. And we only look at the large scale dynamics. So we are only in this graph here. What we're only accounting for is the transitions from that thing to that thing. But we are completely neglecting what happens inside here. So there's some time it takes for information to diffuse in here and then transition. And by essentially multiplying by Laplacian by this factor, what we do is we slow down the diffusion. So we account for the fact that it takes some time for information to spread here. And this is the rescaling step. What this now shows is that we can now accurately compare our new coarse-grained system and rescale system, which we call the renormalized system, with the diffusion dynamics of the original one. So what we did here is, what we just plotted is the probability over time for information to either, like we start at the first cluster, we look how probable it is over time to stay here, to walk to the first cluster, to walk to the next cluster. Our results are the circles, and the original dynamics are the diamonds. And you see a very good match. So yeah, this is basically the procedure, and now some more examples. What we can do with our method, and we thought it would be interesting to look at the brain, because the brain has different hierarchies, it has modularity. So we thought, okay, maybe because our procedure can zoom into the different scales, maybe we find something is interesting. And so we thought maybe we can reveal some patterns, some behaviors that may only become apparent at larger scales. So what we did is we looked at EEG recordings from patients which were involved in object recognition. So they were just shown some images and had to identify certain images. And from each of the electrodes recording, we built a mutual information matrix. So essentially how much information is shared between two electrodes. And from that, we extracted the graph using this method here. And the moment we have the graph, we compute the Laplacian, we compute the spectrum. And what we see is we have a lot of significant gaps in the Laplacian spectrum, which indicate interesting characteristic scales. And we thought, okay, we now look at the first two significant scales. So this side here represents the brain activity at rest. So this was taken 5 minutes before the recording, before the object recognition task was performed, and this is during. And now the interesting thing is that in all cases, we first of all see that the effective vertex here, which it always summarizes the nodes in the occipital lobe, where the visual cortex sits, where visual information is processed. So this is the most central node, which is I think quite interesting. And then what we see is that these effective vertices here summarize large groups of nodes which share a lot of mutual information. In other words, these clusters share a lot of information. So what we do by essentially projecting it down to fewer nodes is we remove redundancy. Also, what we see, which we were told was quite interesting, is, and expected from a neuroscience perspective, that before the task is performed, we can summarize much more. So we can contract much more. And this is just because the brain is less effective in information processing as it is during activity. So during activity, the brain becomes more specialized, there's less redundant information, and therefore we can contract much less. So yes, and then because we have these high clusters of mutual information, maybe this could be used to study coordinated neural activity. Yes, so this is essentially what I said. That during a state of attention, the brain becomes more efficient in processing information and becomes more specialized in handling information. What we also looked is, again, can we preserve the dynamics in these cases, because this is a very, very messy system. And what we saw is that for the brain during activity, we can do it quite well. And this probably indicates that the modes, that the slow diffusion modes, the slow frequency modes, which represent the macroscopic activation patterns, are representing the system across the scales very well. In other words, we have a higher degree of scale invariance. And if you think about this from the perspective of the critical brain, this makes sense as we think that the brain will self-organize itself toward criticality in a state of attention, which is characterized by increasing correlation length and therefore a higher degree of scale invariance. So these are all findings. But I have to point out that this, I think, you can say too, is not a rigorous study of brain activity. It is just a proof of concept in a sense, because we make a lot of simplifying assumptions. The first one would be, we assume that the brain dynamics are stationary because we're just extracting one graph, which is of course not the case. And also EEG recordings are, they're already quite coarse. So probably to get much more interesting results, you really have to be at the neural level to get something more interesting. But we just wanted to show what we could do with our method, and we get some sensible results. So the two major takeaways for today are that we propose a method which simplifies a complex system represented by a graph and gives us an effective representation which preserves both the large-scale dynamics and the large-scale structure. Yes, and this simplifies very large complex systems. And on the other hand, we can use it to study real-world systems like the brain, and then maybe it allows us to understand how microscopic properties emerge from the interaction between the microscopic constituents. But yes, that is it. Thank you.
Thanks for talking. So you know the Villegas paper, the nature physics one, that does something similar. They kind of validate the method on these fractal graphs, right? So they have these like example networks that have scales.
Yes.
And so that's their proof of concept.
Yes.
Method works. Did you do anything like that?
Yes, with the Barabasi Albert we did.
With Barabasi Albert?
Yes.
Okay, so Barabasi Albert is, how is that?
Scale.
Okay, so it's scale free, but
Yes. What do you mean?
what I mean is that they have those weird fractal ones where like
In the new one, not in that one, right?
they do it in the top. They do it in the higher order one, but I thought they also did it in the Villegas one.
I don't think they do it in the Villegas one, but they do it in the other one,
Yeah,
with the fractals. And we didn't look at fractals yet.
Okay.
So the thing is, fractals are probably so. Another disclaimer: this is not a renormalization group. This is just a coarse-graining procedure inspired by the renormalization group. If you want to really get the flow, so you really move across scales, you need something like fractals, because it has certain properties in the spectrum. So that's very important.
You're right. That's what Shivani presented. But like that was a good proof that their method.
That is That's the only, but it's also the only type of graphs where we'll probably work to get something that is very close to renormalization group. But this is not a renormalization group, and everything.
I think that as Roman said, so in discussions with the graph sparks, we expect that some of these dominant roles would be associated to some form of localization. So what was the kind of density of the graphs? So did you have very sparse graphs, or they were fairly dense?
So the first example, so we did both basically. So the first example is to make it a bit more understandable, were very sparse graphs. We just had very dense cluster, but connected by sparse. There by a few edges. But for example, in our brain graph, the graph is full, like it's a fully connected graph. So Yeah. So this is essentially the graph.
Then it's fully connected with negative entries as well.
And no,
It gives mutual information.
yes.
Oh, it's
That's probably why they use mutual information, not correlation.
Exactly.
Then you get
It's a weighted.
Yeah, it's a weighted
So
graph.
what's the Laplacian for the weighted graph?
But a weighted graph.
Yeah.
Would be
Like what Laplacian do you use? It's not that straightforward, right? To have a
no, just a combinatorial Laplacian, but weighted. And the weights,
It's just the A.
so
Yes,
the degrees have some of the weights.
Yes. And the weights are like without weights, of course, everything will collapse in one node, right?
Yeah,
Because everything is the same.
Absolutely.
Yes. But the weights give you sort of structure, and then you can do it because this will change the nodes.
I just wonder what would be the sort of distinct feature of your methods when you say you can select the structures.
Yeah.
You can coarse-grain the networks based on structure.
Yes.
How does it? What's the feature of your model compared with other like structure-based
Yes.
correlations?
Exactly. So the whole reason for this paper is essentially that we can preserve the structure and the large scale dynamics. And the other ones can, for example, the Villegas one can not preserve the large scale dynamics. And to preserve the large scale dynamics, you basically have to adjust the interactions. And what usually these coarse-grained or renormalization schemes do is that they summarize so they just get the coarse-grained nodes, and that's it. They keep the edge weights between them as in the original graph. But you cannot preserve the dynamics because you have to adjust also the interactions between the new supernodes.
What do you mean by preserve the dynamics?
So basically the probability, so this is the original graph, right? The probability for information to go from here to here is not the same as to go from here to here. The probability to stay here is the same as to stay here.
If it was a random walk.
Random walk diffusion has.
Okay. So if it's diffusive dynamics.
Yes. Yes. Only diffusive dynamics. If you want to preserve different dynamics, it's probably not a combinatorial plus. If you have something which is a Gaussian approximation in some sense, then you can still use the combinatorial Laplacian. But if you move out of that regime, you cannot.
Can I just ask about the brain clusters you found?
Yeah.
I was just curious to know if the clusters that you found, because you essentially didn't take into account spatial information of nodes over here, right?
No,
It's just
not at all.
were the clusters you found highly correlated with how close nodes are in space as well?
I didn't check that.
That would just be something else.
Yeah, I didn't check that.
Because I'm interested in how.
But wait.
spatial correlates.
No, yeah. Yes. Sorry, you can see this here because these are the EEG electrodes here, and they're placed in the same way as they were. As they are distributed across the skull. And we see that we have here clusters. So same color means same effective vertex. And so, yeah, they're close to each other. In most instances, there are some instances where it's not a case, but usually this is the case. Yes. But it's very coarse, the resolution. So we don't know. This is not at the neuron level. So basically you have to think the one electrode represents, let's say, a group of neurons, a large group of neurons.
I just check what's on the chat.
There's no questions on that.
All right, then we can thank Marvin for the
Thank you very much.